1, 2. 1. 1, 2. 1, 2. Welcome to the last lecture of CSC 140. How was the tournament? We don't know. We don't know. Did everyone manage to submit last night on time? Or actually in the morning by 9 a.m.? Yeah. Say it again. Yeah. I know. So last the evaluation script that was running during the night, we ran it. Well, it yeah. So it didn't work. But the one in the morning worked. So we have the results. So I don't know why I still didn't track that. I think there was one submission that was faulty in the last night that was breaking everything. But now the one in the morning works. So we have results. Yeah. And I didn't put them. I didn't put them on purpose. I didn't publish them, so we had them. So I'll upload them soon and during the lecture. Now we'll find them out. Actually, before I go, let's go with the announcements first. So the report is due on Sunday. The P4 report. Worksheet 6 is due on Friday, in 2 days. And also do fill out your sets. So we are at, well, I should have changed that. We're at 27% now. One second. And I will give 1 extra credit point for everyone that submits the sets, basically. So yeah. Oh, I'll give everyone a point if we have over something like 80% response rate, something like that. So let's do that. If we reach at least 80%. Yeah. A question there? Worksheet 7 on Canvas.
I think the due dates are messed up. I think worksheet 6 should be good.
Yeah, this is one was also 7. There's a 7 one. Okay. Okay, then don't submit that. Yeah, I'll look into it. I didn't realize. So I'll take that out of Canvas. So that won't count. Worksheet 7. Yeah. It must have slipped from importing it from last year. Any question there? No. The other question. So what's the final thing? Yeah. So we'll announce the tournament winners in the second half of the class. Also, does anyone have any questions about the final we'll have next week? Yeah. It will be. So it will be. So it won't be open book as we had with the quiz, but I'll allow you to have like a cheat sheet that you prepare at home. So like 1 sheet, so like 2 pages, like front and back. Basically, you can I'm expecting everyone to kind of have 1 page basically, so you can like one double-sided page, sheet, and you can put any formulas you want from the course there. But that's it. No electronic devices. Otherwise, like no iPad to check the slides and things. Just that cheat sheet. Yeah. Monday at 4 p.m. It's posted. I'll make an announcement on Canvas. But they are posted on the UCSC exam registrar sort of website. Haven't you checked? Am I correct? It's Monday 4 p.m. if I remember correctly. Yeah. And it will be here in this classroom. So not 5:20. No, not 5:20. We started course will be 4 p.m. instead. I should announce that. Yeah, Canvas. Yeah. Oh yeah. We went through the questions. I went through the questions of my TAs. I didn't actually try to attempt to do them beginning to end to time myself to see how much it would take me. So I don't know for sure, but I would say, yeah. I won't answer this. I don't know. Yeah. Let's. I can maybe post on Canvas if it's really crucial. Like it'll be around 2 hours to 3 hours in general. Yeah. 4 p.m. 4 p.m. on Monday, next Monday. Here in this lecture. Oh, wonderful. So this is Alana, the grader. So she brought the second quizzes that were graded, so you can pick them up. Yeah, and yeah, another question. Yeah, it's good. So in general, for the final, it'll be questions similar to the quiz and the worksheets, but harder. So it'll be because the quiz was on the easier side. The quizzes were on the easier side, so the final exam will be harder than the quizzes, in generally. But it's similar style. Sorry? Oh, they're in my office. So come after the class, and I'll. Yeah, I don't have them with me here. Yeah, or otherwise you can come tomorrow to pick them up if you prefer. I don't have them with me. Well, why don't we pick them up? Those up, or did you put them here? So I'll let you pick them up in the break. In that case, and yeah. Okay, yeah. So if you can come tomorrow again if you prefer. Oh, after class? Or after class now? Yeah. Okay. So, any other questions about the final? So it will be like the quizzes, but on the harder side. So because the quizzes were easier. It will cover most of the course, like beginning to end. Yeah, all the topics. Yeah. Practice problems. Well, it was mostly the worksheets were the practice problems. Oh, kind of, but worksheets are a bit harder, I would say, than the quizzes. So kind of like that, like kind of level, yeah. Yeah. Yeah, like a worksheet, yeah. Okay. Okay, let's start. So if you remember last time, we were covering this idea of variable elimination, where we were, so going back, we were basically computing this marginal over x2 as basically by marginalizing over another variable x1 over the joint distribution of x1 and x2. And this is already applying chain rule over the joint. And then we're repeating that process multiple times for another variable x3, x4, and so on. So, and every time we wanted to compute a marginal at xi plus 1, we were taking basically the joint between xi and xi plus 1, and then marginalizing over xi. And here, this is already applying, this is basically the joint distribution between xi and xi plus 1, but already expressed using chain rule as p of xi times p of xi plus 1 given xi. Yeah, and then we saw how basically we can decompose a long chain of variables by for example, choosing to take one variable, say a, and eliminating that. And basically by eliminating, we basically move all the other terms that do not depend on a. We move it outside the sum. And this is basically applying distributivity. This is basically applying the distributivity rule, which I'll write it on the board, just make sure. I know you know it, but where's the sponge? So it's this, so by distributivity. I mean this A times B plus C equals AB plus AC. So here we distribute one number over sum, and of course, if you have many, so here this A is being distributed, is shared between the sum, and then is distributed over each of them. So this A is common. So and in our case, it's the same thing. These terms are what we have as the A there, and basically they are common in all the other factors. So we apply distributivity for at large scale for all these summations, for the entire summation over A here. Okay. So let's see an example. So if we have a network with 4 variables, so for example, the grass is wet if the sprinkler is on or if it rained. And maybe the rain can be caused by the weather being cloudy. And maybe the cloudiness also affects the sprinkler in some way. So we have, in that case, we have the probability of a wet grass, the probability of observing the grass is wet, is now a summation over all the other variables over the rain, sprinkler, and cloudy of the joint distribution. This is the joint distribution. That term is exactly P of wet grass, sprinkler, rain, and cloudy. It's that joint. And then by applying the structure of the Bayesian network, by these independent assumptions, we can write the joint with this factorization again. So we write it as P of W given R and S, P of R given C, P of S given C, P of C. This is what the network tells us. These are the conditional independence assumptions that the network tells us, that this joint can be factorized like that. So we have this, and then we decide to eliminate one of the variables, let's say C. So in that case, what we mean is that we take all these factors that do not depend on C, which is this one, which is P of W given R and S. This does not contain C at all. And we factor that, we distribute that like here. So this becomes our A here, that's factor. P of W given R and S here is a common factor, we distribute it. And then this becomes a factor over C, all these terms, including the summation. And then we eliminate that. And we say that that's F of a factor over C of R, S, and that's it. Yeah, of the remaining variables that are not C. And this is basically the factor after the elimination of C of over R and S. And it's a function that basically tells us what, for particular values of those variables R and C, it tells us what should be this whole equation, this whole term in red. This is what it is. It's a function. It's like that tells us, gives us the probability of this whole term basically, which is still a probability. And it has parameters R and S because for each, whether R is true or false, whether S is true or false, it will have different values at the end. Does it make sense? Any questions? Okay. Yeah, so this is how they look in practice. So this is how these probabilities look. So for example, we start from these conditional probability tables for each of these terms. So we have a probability over cloudiness, whether it's true or false, 0.3 if it's true, 0.7 if it's false. The probability of the sprinkler being on given that it's cloudy, we have all these probabilities. The probability that it will rain given that it's cloudy, again, all of these probabilities, and then the probability that the grass will be wet given that the sprinkler is on or whether it rained. We have all these probability tables, and this particular term in red is this factor is basically computed like this. So basically we have this big table here where we take, for example, all the possibilities for R, S, and C, all the possibilities, whether they're true or false and so on. And this is for binary variables. So, and we multiply the probabilities together. So we compute this term, P of R given C, P of S given C, P of C, these multiplications as you see them here, and which we take from these tables. So for example, the probability of R given C is 0.4 because this is the probability of R being true given C is equal to true, which is 0.4. So we take it from this table and we put it here. And this one, P of S given C is this one, true. So it's 0.2. And this is P of C equals true, 0.3. So you see, we take all these numbers from all these tables and we compute a factor, the table for the factor. Once we have the table for the factor, this is with respect to, this also contains the variable C, then we have to marginalize over C because we have a summation over all the values of C, which can also be true or false. So then we get the final table for the factor, which only contains variables R and S. And here we got, for example, 0.031 by summing over, for this particular case where R is true and S is true, by summing over all the values of C, which are true and false. So these two values. So 0.024 plus 0.007 would be 0.031, which is this number here. I'm stopping here for a few seconds. Does it make sense to everyone how we compute them? Yeah. Yeah, these ones here, you mean? Yeah, so we're trying to compute this term in this big circle, this big term here, the red circle. And we have this table that we compute with all the values. We have all the values for R, S, and C. True, false, true, and so on. And these are the values here. And then we have to sum over all the values of C, which can be true or false for all the possibilities. So this one and this one get added together because these are the values of R and S are both the same. For this case, for when the R is true and S is false, these two cases will again be summed together. 0.096 plus 0.063 is 0.159. Does it make sense? Yeah. So we summed up over each of those pairs of numbers because we have a summation over all the values of C. We are marginalizing over it. Yeah. Okay. So this is how the factor looks like. So it's a function which for all the possibilities of R and S, and here they're all binary variables, we have a probability as an output, which we have, and this is this whole sum in red. These are the values of that whole summation of this term. And we repeat this thing again. So there will next time we eliminate another variable, let's say S, we'll get a different table like this. We do the same thing again. We get a new table, this big table, and then we get this marginalized table. And again, we repeat this procedure again and again for every variable we eliminate. Okay, so let's see a more complex example. What if we have this network? And this is a famous network proposed by Judy Pearl back in the 80s about diagnosing tuberculosis or lung cancer. So the idea is you're trying to diagnose tuberculosis and lung cancer. You have also you have some information whether you visit some infected area. You have information whether the patient is smoking, whether they have bronchitis, dyspnea, which is shortness of breath. They have abnormalities in the chest ray. So these are all potential tests you can do. So sometimes these variables are not necessarily observed. Maybe they observe, maybe not. We might not know the values of them. Say an X-ray, maybe you haven't done an X-ray scan yet. Can you still diagnose tuberculosis without an X-ray scan, for example? But say if you have an X-ray scan, how much more information does that give you in the diagnosis of tuberculosis or lung cancer? Or for example, how does smoking affect the risk of you developing lung cancer? Or how people in the medical community call it modulate, how smoking modulates this particular disease. It increases the risk of it. So how do we do? So let's say we want to compute the probability of having dyspnea, the D, this variable here at the end, D, dyspnea, shortness of breath. So we need to eliminate all these other variables to compute this marginal over P of D. So these are our initial factors. And this is exactly, if we multiply them together, this is going to give us what exactly? Somebody? Can someone tell? What are we going to get if we multiply all the factors, all these factors? Yeah? Yeah? The joint distribution of all the variables. That's what's going to give us, yeah. So by multiplying all these factors, it's going to give us all of them, like P of V, comma T, comma A, comma X, and all of them in the network. So that's the joint, if we multiply them all together. So we start from the joint, which is factorized like this. So also this was also a joint distribution in the previous network, again, which was factorized. So now we have the same thing with the joint that is now factorized, and we eliminate, let's say we choose to eliminate V. So this term and this term are the ones that depend on V. Everything else does not depend on V. Hence, they can basically, they can basically pushed outside the summation over V. So our factor FV of T is summation over V of the prior over V times the likelihood of observing T given V. Again, and this is, it's the joint of T and V. V is marginalized, that's what we get, only T. And now we basically replace these two sums with a factor, and everything else, everything else still stays, basically. So now our let's say our joint becomes this now. And now we eliminate, now we eliminate a new variable, let's say S. So we look at all the terms that depend on S here, which are this one, this one, and this one. And we form a factor with those three terms. And we sum over S again, we marginalize over S. And this becomes a factor of all the remaining variables that are not S there. So basically all the remaining, what are all the variables here that are not S? Well, it's just B and L, right? So this new factor will depend on B and L. And it's a factor obtained after elimination of S. So now, this our joint now becomes F of the previous factor over V after limiting V, sorry. And now the new factor after eliminating S of the remaining terms. And then we do the same thing for a new variable. Now X, we eliminate X. Which are the terms that depend on X? Only this one. So we form the factor. F of X is basically we marginalize over X with this term. The only remaining variable here is A, so this factor will still depend on A now. And we replace it in the distribution, in our distribution. Now we have this. And we do the same thing for the remaining variables for A, T, L, and D, and B. And we keep doing this process. And that's how we get P over D. Actually, we won't do it over D, because that's what we have to find. We won't eliminate D at the end. We'll just be left with D. We eliminate the other ones. We eliminate A, T, and L. Yeah. Oh yeah, because this term here, you see, this is this is a marginal over marginalizing over X of a conditional distribution of X given A. This is a distribution. And one of the properties of distributions, what was it? Do you remember one of the key properties of distributions? They sum to 1, yeah. So all the elements in this distribution have to sum to 1. So if we sum over X over this distribution, we'll basically get 1, because the distribution has, it's basically, it's a simple case, it's a simple factor that is always 1 for all values of A, basically. That's why you get this. And the reason why you get this is because you don't have another prior over A here that you have included in this factor. You see A appears in other terms, but it's not it is not here. It's not present in this particular factor. So that's why you get this. Yeah. Any other questions? Okay. So we eliminate T and so on, the same process. And then we eliminate L. These are the factors that depend on L. We form the factor. It's only going to be dependent after that on A and B. These are the remaining variables. So we get a factor of A and B. And now we eliminate A and B, basically. And we get this. So we compute FA of BD, which is this summation over A of this whole thing. And we get a new factor FA of BD. And then we simply, finally, we eliminate over, we get FB over D, which is another elimination over B. It's another marginalization over the B variable. And that will be the factor over D. And this is P of D at the end. This will give you P of D. Yeah. So we can see a variable elimination as a series of rewriting steps. We rewrite those terms as factors. And now this is mathematically how it happens, but in practice, what this means is that you will write an algorithm that basically does those summations in a particular order. So actually that means that when you compute a factor, you have a for loop in your Python script. You loop over all the values of, so let's take an example. So here, let's say this last factor here, because it's easy. So we have to marginalize over B. So in your Python script, you have a two-dimensional table for all it will have two columns, one for B, one for D for all the values, and you have to sum over all the values, over B. So you'll have a for loop in your Python script that goes over all the values of B and sums up together, and it gets condensed table just over D. And you do these Python for loops for each variable in turn. How do we deal with evidence? So what happens if we're given some information in the network? Let's say, for example, we have a patient that we're trying to diagnose with whether they have tuberculosis or lung cancer, and we know some values about their medical data. We know whether they smoke. We know this variable. We know whether they visited a risk area of tuberculosis, and we know that they have dyspnea here. We know they have shortness of breath. So given these informations, how do we find what's called the posterior over lung cancer here, L? Well, how do we find the posterior, given these information about the patient, how do we find out whether they have lung cancer? What's the probability that they have lung cancer? Now, given that we have these three informations about this particular patient. So we start out by writing, again, the same factors as before. But now, whenever we know a particular variable that is instantiated, like V, the visit to a risk area. So here, say we know V is true. So basically, this person did visit a risk area. They have visited. Then we form a factor with that. So basically, we form a factor over P of V, which is P of V equals T. So it's simply a constant. And the factor over P of T given V over t is basically p of t given that visit is true. So the conditional distribution of t, which was tuberculosis, given that they actually visited a risk area. So we select the appropriate part of the original factors given the evidence, and we form new factors by selecting the parts with the right values. So this is how we start. So we rewrite all those all these initial factors by we instantiate the factors where we know information, like these three. For these three nodes, we know their values. So then we build factors over all those variables. So we have a factor over p of v, we have a factor over p of s, we have a factor over t given v of t. And the reason why we have a factor here is because we know something about the parent variable there. So even though we don't know the value of tuberculosis of t, which is tuberculosis, we know the value of v, which is always true. The v was true here, so that's why we form a factor here. We form another factor, L over s, because we know s here, have information about s. We form another factor here, p of d given a and b. So that's here, d given a and b, because we know the value of d. So then that table gets restricted to only when the value of d is like here is true. And then we do the same thing again, like as before. So we start eliminating the variables. Let's say we choose to eliminate x. So we look at all the terms that depend on x here, and it's only this one here, p of x given a. So we eliminate that and we form a factor, f of x of a. Yeah. And then we eliminate a new variable, let's say t. So here, this factor and this factor depends on t. They are the only ones here that depend on t. This one and this one. So we form a new factor, which after eliminating t of the remaining variables, which are a and l. This one didn't have anything else left. It was only t. Then we eliminate a. These are the factors that depend on a. We eliminate it, so we get only a factor over b and l, and so on. And we eliminate b, and up until we can compute this and get the result. So what will this final thing be? Will it be a vector? Will it be a scalar? What will it be? What exactly is that? Somebody? It's a scalar. What is it? What does it mean? No. Yeah, but what does a scalar represent? What will it represent? Exactly this. The probability of L given these. Well, this has been given here, but it's yeah. This is what we wanting to compute: P of L given V, S, and T. V, S, and D. Yeah, that's what it means. So this will give us what will be the probability, the final probability that the patient will have lung cancer. It will be a single number that we have to get at the end. The probability that lung cancer will be true, let's say, or both, or the whole yeah. Well, also when it's false, we'll know. The false version is 1 minus the true one. Okay. So in particular, one key aspect about variable elimination is that we have to select a good ordering of the variables. Sometimes to reduce complexity, sometimes the order in which we select these eliminations, whether we choose X first and T second and so on, or whether we choose a different variable first, that will impact our complexity sometimes, because the resulting factors can be bigger or smaller and so on. So sometimes there's some thought that can be put into finding a good elimination ordering. but we won't cover this in the class, so like kind of which is the optimal ordering and so on. Okay, let's take a 5-minute break, and then we'll announce the terminal results, and we'll give a conclusion. And you can come and take your quizzes in the meantime in the break. So, yeah.
Quiz once, I forgot to ask for yesterday.
Oh, come to my office anytime, even after the class. After the class, if you want, because I'll have to go. Alana will come to bring a ticket. Yeah.
Sorry about that.
No worries. Yeah.
Programming for bigger, like the result, because I don't know, like have like a really many one defeat the extra agent, even the
Oh, it's no, it's okay. So I think because for the tournament, you mean?
Yeah,
Tournament?
It's the minimum line for getting the 4 point.
No, I think the key thing was that you had to beat those staff agents, kind of, and like those three staff agents.
We based the baseline, but we didn't beat the extra agents. Even like in the top line, I think
I'm open to curve it. I'm open to curve. Yeah. So that's a problem. Yeah.
The last
Yeah. Right.
It's like it's out. It's like
Right.
But those results they show are
like last night. You mean last night? Yeah. No, I know. The last night the script failed, and I was looking into it. Yeah. Oh, we'll talk. We'll see. Most everyone apart from 2 teams got only 2 teams got the zeros, because I think the script didn't load or something. So again, but everyone else got it working. Only 2 out of 30 something. Yeah. Oh, we'll talk. I think you can. Yeah, we'll talk. We'll talk after the class. No, don't worry. We'll Yeah, they can print it. Yeah. Double one single sheet, double sided. You can print it. Yeah.
And how long you haven't decided yet?
I haven't decided yet. I wanted to go to the quiz, not to the exam myself, and see how long it takes me to do it, and then I'll decide on the final time. So yeah. It's in my office, but if you come after the class, because I'll be going to the office, you can come and pick it up. Yeah. Oh yeah, well, yeah, no, because we just had it on she needs a bit more time to kind of grade it. It might need like a week, so we'll see. I'm open to leave it outside my office, or somewhere and you guys can pick it up next week, something like that, anytime. Yeah, but yeah, I know. Don't worry. It'll be okay. Yeah. About the report, yeah, I think there was a structure somewhere in the spec. You had a bit of bullet points, 5 or 6 bullet points. Let me look into it. I know because somebody asked on Piazza, and I didn't manage to get on that. Yeah. Yeah. It worked, yeah. The second time, yeah.
That's the first time.
I don't know. I think somebody submitted some file which crashed the evaluator function. Yeah, because we had some error, but and the second time it worked. That worked. Yeah.
Hopefully ours worked.
Yeah. No, I think most of them worked. It was only 2 teams that didn't work out of 30 something. So yeah,
2 teams.
2 teams. Yeah, yeah. Something didn't work. Okay, shall we start? Before we go into the tournament, I wanted to make a short announcement. So for the exam, I got already a couple requests for people to take it on Zoom, over Zoom. So, and I had one also in the chat just now that I saw. So I'll be a bit more strict than with the quizzes on the Zoom. So basically, I won't generally allow it unless there's like a really major emergency. Like for example, if you're really sick, and if that's the case, then I would need to see like a doctor's letter on the exam. So if somebody, otherwise I won't be as flexible as I was with the quizzes because it's a final exam. So I want everyone to be here unless of course there's another storm coming and they close down campus. Yes, we'll take it over Zoom, but otherwise we will be taking it in person. So the only really exception I'll make is if I see a doctor's letter on some medical leave, and that will be sort of some point over the weekend of Sunday or a day before. If you have flu now, for example, I hope you'll get better by Monday because it's 5 days. So okay, so that's the policy we'll have. On the tournament, okay, let's going back to the tournament. So so as I said, we had some trouble when we ran it overnight, but when we ran it in the morning after I ran it at 11 a.m. 11:30. So basically, if you submit it before that time, you will have it in now. And then I haven't published them yet on purpose to announce the winners in the class. But I'll copy it afterwards. So after the class, you can still check all the GIFs and all the matches, and you can have a look on them. Okay. Let's see. So let's start with the 3rd place. So the 3rd place. Sorry? Excluded. The staff is excluded. Yeah. Have you seen the results? No? Oh, yeah. Excluding the staff, excluding. Okay, so drum roll, third place, nanoslugs. Can you stand up? Who's seen nanoslug in the class? Okay, congratulations, the two of you. Do you want to say a few words of how you designed your agents? What was your strategy?
So we would anticipate where the ghost would come from the defensive agent. So on the offensive agent, there were a mix of weights. So we had, it would chase the closest tube, but if there was a ghost nearby, it would obviously avoid it. And if there is a capsule and a ghost chasing it, then it would go after the capsule. And if there was no ghost, it would avoid the capsule, because we only need the capsule, like when there's a ghost chasing it, so we can eat it. Yeah, that was like how we did it.
Yeah.
Yeah.
Nice. So you can ask them more details after the class, if you want to check. Second place, okay. Drum roll. Ghostbusters. Who's the Ghostbusters? Can you stand? Can you stand up? Team Ghostbusters. They're not here. They are busting. Yeah. Are they on Zoom? Maybe. Are the team Ghostbusters on Zoom? No. Okay, so we don't have them here in class. Okay. Yeah. Also, by the way, so I do encourage you, because they're not here to tell us their strategy, I do encourage you to share your strategies, for example, even on if you have any private channels like on Discord, or if you ask your peers after the class, do, ask them how they did it. Great. First place. Ooh. Team Ghost Slayer. Who is that? Just you in here? Okay. So that's who is the third member? He's not here. And what? Okay, well, congratulations. So, what was your strategy for the two agents?
I made a estimation on offensive and defensive agent. So I also made a trap for defensive agent, so you can trap enemy.
You made a trap for the defensive agent.
Yes. So we never get out, and I think it just one time.
How does that work? How does the trap work?
I check if I use a uniform concert. If it's a little hard to explain. Like, can draw the board.
If you want. Yeah. So applied uniform cost search on
For example, there's a icon here. That goes here. So I check use uniform cost search. Check search all the surrounding, like all the paths for the pipeline. And if I find the node is my goal, I just continue, which means that the search result won't return directly. So I return the visit node by space, the pipeline symbol just disappears. So if only one
you should expect the whole class, because yeah. Is this the offensive agent or the defensive? The defensive. What about the offensive one? How does that work? Does that? Interesting. Yeah. Interesting. I don't think they get it yet. Yeah. It's okay. It's okay. So don't worry.
So the space here is the pipeline can be removed. So, for example, if pipeline will go up there,
don't worry if it's don't worry. Well, we can ask him after the class. Yeah, no worries. Yeah. Nice. So this was the this was the final ranking. Yeah. So I was wondering if the second place was the same team or different team. It's a different team. Damn. I thought IRL just meant a different algorithm. So I thought it was the same team. Oh, so okay, so we have okay, so apparently Ghostbusters IRL was a different team than a Ghostbusters, which was number 4. So I didn't I thought they submitted by mistake the same. Okay, so let's see Ghostbusters IRL on the place 2. Yeah, get up. If you're gonna clap. So how did you solve it? How did you?
We just used I feel like it was an easy strategy.
You explain to everyone,
So,
not to me. Yeah.
On offense, as long as if there's a power point remaining, or you have 4 behind the points, both our agents will go on offense no matter what. They just ignore defense, just always go both offense. And then as soon as we're at the end of points, both of them will draw back and defense.
Yeah.
So
the theory behind that is that most people are using the default 1 baseline, 1 defensive agent. Then we could quickly build a lead and then stay back and stop them from crossing overall. So that was our strategy.
So yeah, we looked at the other teams and it was like most of the teams are doing 1 offense, 1 defense. So if it's 1 offense versus 2 offense, well, the 2 offense is going to always be more good than 1 offense, right? And then so we're just like, okay, we just base our strategy on counting other agents.
Yeah.
And,
It's really cool. It's really cool. It worked. Nice. Very good. So them and the first team, Ghost, they are the only ones who beat the number 3, the staff agent, one of the staff agents. So very good. Let me correct that in that case. Let's correct here. So we have Ghostbusters IRL. And then Ghostbusters. Yeah. So actually, let me see. So I can show it now. So I copied now the results. So basically now we can see all of you can see it on the phone, your phones as well. You can see the final rankings. So if you log in also on your phones, you can check them or after the class. But this is the full ranking. So there were only 2 teams that didn't, that still had some errors in the script and couldn't be run. So do contact me if you any of these teams. Do contact me afterwards. So we sort it out. Oh. Yeah. So you can look afterwards on all these matches and see how they've done. Team Ghost Slayer. So let's see one of them. So what if we see this match, for example? They tied. So what's this? This is a tie. The third column is a tie. Is that correct? Team Ghost Slayer. What about if we see this one? -1, 3. I didn't manage to look on these results. Indeed, I just seen it for the first time as well. Yeah. 16, this one. Wait. So this is the match between the first team and the second team. Okay. You can look at them at home and for each of them, but they're not published, so I just to publish them. Okay, going back. So okay, so to wrap up the class, what you might be wondering, what are the next steps now that you took this AI class? What are the next steps that you can do in this direction? And when the next natural step is to go into machine learning. So we have here at Santa Cruz, we have several offerings in machine learning. So we have CSE 142, CSE 144, and some other ones. I just listed these 2 for now. Are any of you already taking these courses? No, you took 144 before. But basically, this is the next natural direction for you to continue on this. Where you do machine learning, it's much more focused on a bit less on working with graphs and more, kind of working with statistical methods. So you learn about kernel methods, so you see, I copied the syllabus for the 142 class. So here it contains so we review linear algebra, probabilities, then you learn about regression, loss functions, gradient descent, which are really fundamental concepts in general machine learning. You'll learn about linear classifiers, perceptrons, separate vector machines, many things like decision trees, clustering methods, space maximization, boosting and reinforcement learning, and then finally neural nets. So all of these are topics that will be covered in a machine learning class if you choose to follow this direction in AI in general. This was again an introductory course in AI, but there's much more. We've barely scratched the surface. There's much more going on. Here are, for example, some key applications of AI and machine learning that are currently in use in today's world. So for example, we have image segmentation. These are kinds of These are algorithms that basically, from an image, they can basically give us a segmentation, tell us what are these, each of these, like, this is one person, this is another person. They identify the people, the objects, they track objects like cars and so on. And this is basically telling us which pixels belong to which object. This is what a segmentation problem is. It's a very fundamental task to do with the AI and machine learning algorithms. They do 3D reconstruction kinds of methods. So you can basically use this to reconstruct 3D objects. You can even use it on medicine, on medical scans to do what's called image registration, when you align images together. Like this is the case of brain images here. So you have two from, say, the same person today and also 1 year later. And then you basically align them basically so they are basically in the same reference space. I mean, in particular, I've worked a lot on the image, medical domain. Obviously, I've used a lot of the AI methods for doing automatic diagnosis, prognosis, and use it to predict the future evolution of things. Obviously, if you have somebody in the hospital, they the algorithm predict what's going to happen to them in 6 months, in a year, in 5 years, to like future prediction. A bit like using AI to predict, let's say, the stock market, like kind of like what a temporal prediction of the same in medicine with patients. So diagnosis, prognosis, all these kinds of treatment recommendations, having an AI tell them, advise the doctors what the drug should a patient take, and so on. Some key applications are also, for example, in natural language processing. So working with text and images as well. So, and this is something, again, we haven't done in our course, but you would do in a more sophisticated, like machine learning class, maybe even one which is more applied, for example. So, and we do offer natural language processing here. So this one is CSC 244B is being offered for this one. So for these diplomas, you would take 24064, and these are all grad courses. For example, they have some undergrad courses that I mentioned earlier that can cover these. So in natural language processing, you basically work with text. You're trying to understand text. So for example, you can make systems that basically, given a text, like a cute little dog sitting in a heart, it basically generates an image that represents that text. Or a dog walking next to a little dog on top of a beach, again, it generates another image with that. So they understand text and images together. So there's a lot going on. There's a lot more going on. We've barely scratched the surface in AI. And here's what I wanted to talk a bit about, some kind of open problems that are in artificial intelligence, and where basically the systems are not yet working well, and where we still need a lot more work. So one thing is still, like, I would say text understanding is still something that doesn't work well. So you probably have seen recently the announcement of GPT, the model. So there was GPT-4 was just released yesterday. And on the most sophisticated models we have right now that understands text. So you see, how many of you have tried to play with ChatGPT? Okay, so some of you. It's really interesting. It's really, you've seen kind of like how powerful it can be, but nonetheless, sometimes it's still like missing some things. Like, and so this thing is something that I have to update. So I had this a year ago, but with the new models, I think they do have some kind of, they're starting having some kind of common sense knowledge, but yeah, they still make mistakes. An example that I remember last year, there was a year ago, Gary Marcus person who tried to ChatGPT, and basically said like, oh, you take a mug, you put some water, some tea, sometimes Coke in there, and it was a text like that. And they said, and asked ChatGPT to basically complete the text. And the model said, you are there. The model thought that was poison, but it wasn't poison. TV, so the model didn't realize that from TVs and some Coke and some water, you would die drinking that. But the model, the structure of the that we made like you actually an example of kind of lacking common sense, in some sense, you wouldn't die. The model didn't understand that you wouldn't die from drinking water and yeah. So complex vision tasks are still sort of not properly solved. So and this is something again we haven't spoken about vision, but if you take a course in computer vision, we would cover more on that. So there's some problems like object permanence is still not being solved. How many of you know the context of with the Pikachu game? The Chickaboo sort of Chickaboo. When you do to a baby, so you hide your face, and the baby is so surprised basically because like a 1-year-old, if you disappear behind your palms, then the infant is so surprised, and that's because they don't have what's called object permanence. If you take disappear, you have something they don't have method model in the mind that you actually is still there because so they just find another object. They don't have it. It disappears across the eye. That's something that is still not. I'm just giving some examples, but it's not. This thing is not properly solved. Yeah. Yeah. So
I'm a poor college student, can't afford to take any more classes. Just like
yeah. So if you're not taking any more courses in the university, about it. You can do online courses. So you can basically do it on Coursera, you can do it on that platform, and then you can do more advanced ones. That is, the basics of AI. Yeah, online. Or just work with something that is here. That would get it. So visual navigation around the world is still not solved. So for example, we still don't have self-driving cars around, all around us. Like companies are working on this, but they're not there yet. So basically the technology is still making it's still causing some issues. There's still accidents that happen. So the technology is not yet there, but they should be, which I hope we should have it soon. Some other kind of open problems are more about like learning through action sometimes. So basically, sometimes the interaction of the robot with the environment is too rudimentary sometimes, and like for example, this example here, we cannot easily explore streets without getting stuck or hit by another car. So for example, if you have a robot and you leave it to roam around, it would kind of get stuck, or it would it would not easily. It's quite difficult to make it so working in a super complex environment on our screen and so on. So we still have some work to do on that. Mathematical proofs. So I have here current AI systems are currently at the level of a 9th grader. This is at least from around 4 months ago when I was looking into this. They can solve some and improve some kind of mathematical theorems and so on, but they're still not complex. And that being said, on the left, some systems for some big problems they have been used. Even conjecture. So there was a famous example of the early 90s when a conjecture was used by AI. And I forgot. I think I mentioned it there. Like chemistry, we know about the reason. Does anyone remember? Anyway, so they can be used. AI systems can be used to do mathematical proofs, but right now they cannot do very sophisticated ones. Robotic manipulation. So basically, kind of like having robots that can do complex tasks like cooking a meal and so on. We don't have robots that basically can cook us like an omelette or some favorite recipe. So that's something that we still have to work on, and future AI systems I hope will be able to solve these. to write computer programs or other high level thinking. So we don't have a AI system that can write other specific programs. I asked the ChatGPT a few months ago, and I was trying to ask it to write the spoken algorithm to write the bubbles with Python. Can you write the bubbles in Python? And generally Python code, it had the right structure, roughly, and it was a very simple spoken algorithm. But it was like the code structure was roughly there, but there was some bugs with the using. If you get one index wrong, you can rate it it will work. So I think that code is generated and put it in Python. It was compiling, but it was confusing by that. But this is on the actual code as follows. More complex, like that's only your one of it. It won't do it. So this is what I mean by high level thinking. So doing these high level complex reasoning tasks, they cannot do it. So also there's another problem with energy efficiency of a lot of these models. For example, our brain right now consumes 20 watts of energy, which is around like 50,000 more efficient than the supercomputer Snelius that was bought by the Netherlands in 2021. So basically, these our brains are so energy efficient, and when we build these huge models, sometimes we need to run it on these supercomputing hardware. They consume so much energy. So we have to make also improvements in how to make our AI models more energy efficient. So let me finish in the last 10 minutes a bit and talk a bit about some schools of thought for reaching AI, artificial general intelligence. So let me say a bit. So the artificial general intelligence is kind of like an umbrella term. It's sort of like basically saying, when will AI systems reach the level of human capabilities? That's what AGI. As people have high expectations for it. And it's sort of like different, I would say, schools of thought right now in how to approach this, what kind of work AI should be put, to achieve it, or using what kind of methods. So one of the schools of thought is on scaling. So one of the, I would say, the mainstream school of thought right now that we have is that we have to scale the problem. The way to make it better and better AI systems and scale them is to make it more accurate, to scale the problem. By scaling the problem, I mean having models with more parameters that can see more and more data, 10x more data, 100x more data. You can 10x more parameters, so for example, the GPT-3 model has 175 billion parameters. That's a very complex model. And this is right now the current school of thought. So we need bigger and bigger models and data and so on. And it's been the main strategy since 2012. And this has not always been like this. So before 2012, there were some other kinds of schools of thought and how people, the research community thought we should achieve AGI. Another school of thought, very prominent, is to basically imitate the brain. So basically, this idea here is that nature has already given us a solution to intelligence, and it's in our brain, in our mind, right? So all we have to do to create AI systems that better and better is to imitate the brain. We have some other solutions. We have it. And this school of thought is like basically researchers study neurons in a wet lab, and they study how neurons learn, how they form connections, how they learn, how they solve problems. We have a big research group working on what I call brain organs. There are basically many brains that are many brains that are grown. They have neurons together, they can kind of take and link each other, they form cortical layers. Just as they form the brain, they form layers also in can see how they form, what the visual is and so on. So, and you can study that and basically get inspiration from that to build that AI. So that's another prominent school of thought. Actually, and particularly, I should mention here, spiking neural networks are a particular type of model. We haven't covered it, but these are kind of models that simulate neurons, and basically then they can make predictions. With those and these neurons have action potential. They simulate how neurons send spikes and how that spike travels from synapses to other neurons, and how the other neurons get excited by the spike and so on. And so on. We call this avalanche of spikes that are being sent to so that's another research direction that is quite prominent. And I would say even a third one that is quite a third school of thought that is particularly important, how people think AI agents, AI models and agents should have, is what's called embodiment. So sometimes, and here the idea is that the ML model or the AI model needs to have a body. It cannot, it shouldn't exist just by itself in a virtual world. But you should give it a body and let it explore the real world instead of having it so we're building a lot of times these kind of systems we use it's on the course, logical reasoning systems. We make logical inference, with knowledge bases, for example. But that's not based stacking, that's stacking knowledge base. The idea is that you have to deploy that system in a robot, let's say, and let the robot explore around the world and basically learn more and more and improve itself. So that's these are for example, these are the kinds of robots you see sometimes by companies, for example. So they put them in public places and they just go around and they explore and they learn. The key concept is learning. So you learn more and more. And this is so this is an example of and this generally has inspiration from cognitive science, where you have babies that actually play around with see the baby on the beach, they play around with toys and so on. That's the same idea. Kind of the model shouldn't be static. It should be learning and playing with the environment. So an example of this is, for example, how when DeepMind, when they trained growing up with new agents, play chess, just like they did with Pac-Man. Grow and share and so on. They made the game, the agent play themselves. Two agents, same agent, and they were playing against each other. And one of them was getting better at the point, and then the other one was, I'm losing for this one, right? And then each getting better off each other, basically. So they were all basically improving, just like two kids playing together with each other and kind of and learn from each other. So these are all ways in which we can make the AI agents better. So I don't know if any team tried to do this idea, to actually try to run two agents against each other. Has anyone tried this, to run two agents of the same team? So if they and I think that agents with that how does that work?
So basically, we work on different at the beginning. So they just fight against each other theory, and then we all that. Right. Yeah. What way should that be? Something you learn? Well, from the people. Yeah. Yeah. You see, they just have one agent. And they said the best one on. We can automate this process. We can automate it when they can automatically improve, play thousands of games against each other. And so they improve and get better and better. So yes, so embodiment. So the idea is also to have a body, to put it also in the agent, to put it in a robot, and let the robot explore the world and learn more and more. Any questions? Any general now philosophical questions about AI? Yes.
Kind of a logistics question about learning,
Yeah.
what does it pay attention? If we assume that it's more like a lot of stuff when we walk on the street, and there's no we like have a certain goal in mind. So how do we choose what to pay attention to and what to learn over there's so much stimulation?
Yeah. How does our brain do that, or how does the robot? How does the robot do that? Yeah.
I think they just ignore that and take like what we want.
Yeah.
Like it wants to learn as much as it can. So how does it?
Yeah, it's generally embedded in the application. So the question was, how does the robot learn from the environment? So say if the robot is working on the street, and how does it actually learn? And how does that basically that something that is inherited in the learning process or the algorithm of the robot. So we decided to define this. Basically, then the development technology is going on. You have a robot and really take action, but over the exact like you have to find a way to update those the model there, which are basically to learn the policy and the and the value. That's the learning process, learning the optimal policy towards the goal. Yeah, first define some goal, and then after that, then basically run like like what we studied the MVP, so like MVP to do value and policy iteration. And then that what we learn is basically the policy, and the policy tells you what action to do on the policy. So that's how, for example, to the
It kind of has like an icon.
so that's one thing, you have to kind of have some predefined goals in mind, yes. And sometimes defining the goals is not easy actually in AI research and technology research. And there's actually a whole subfield, the focus expression on that, on how do you define goals. Because for example, like I want my goal to I can't say that, I can't say that goal, everyone understands. It's a pretty long that this concept is a very important series of actions, like go to the fridge, open the door, grab the eggs, put them on the counter, open the eggs, different time. Series of actions. This is what we do all that, but it doesn't even know. If I show you the picture with knowledge, you won't know how to do these actions. You won't know how it got there. How did it be, right? So so even if they define the goal itself, they define what the knowledge is, what the end result of knowledge. It's not easy. It's not easy. And after you define that, how do you learn how do you get that goal? How do you learn the policy? Whether the act that is taking open the fridge, they're going to go hand, track the eggs and so on. Those are all complex actions. Robot. The robot cannot do that. They can do some basic thing. They can grab an object and put it somewhere else, but they cannot coordinate. Well, that's the recourse. Okay. You're welcome.
I wasn't here when the first you were supposed to distribute it. Is there a way I can still
Come with me now because I have it in my office. All right. So if you wait 5 minutes, I'll. Okay. Yeah. The reports?
Yeah. How the structure?
Yeah. So I'll answer on the piazza. Yeah. But send me a reminder if I don't do it. By tomorrow. But, yeah.
Example that you gave with the tea and stuff, where I can understand.
Yeah.
Reminded me of about some recently where they ask it. There's a common trick question with what's heavier, a pound of feathers or a pound of bricks, or a pound of feathers, a pound of steel. Where the initial thought is, the steel is heavier, so steel is heavier.
Yeah.
And if you ask it that, it says, the steel is heavy. It says, they're the same. It's a trick question.
Yeah.
But if you ask it what's heavier, pound of feathers or 2 pounds of steel, it still says it's a trick question in the same way. Because it's just seeing the price, right? It's just there's the statistical.
Some of these things, yes, they are, yeah.